So, firstly, I'm going to introduce the great advantages brought by wireless charging on consumer market. Then, after a brief system overview, I will describe a quite conventional architecture and all its drawbacks. Finally, I will propose a power receiver architecture which further improves the power conversion efficiency, as it will be shown in the last section by experimental results. So, actually, each one of us owns several portable devices, each one equipped with its own power cord. And forgetting the right power cord is perceived as frustrating by most of consumers. Therefore, by wireless charging, power cord is avoided, and by a single grid-connected magnetic pad, several devices could be simultaneously charged by simply placing them on the pad. In order to promote the complete interoperability between chargers and devices, independently of manufacturers and brands, a universal standard has been developed by the Wireless Power Consortium. But unfortunately, the power conversion efficiency of such a system is relatively poor if compared with traditional methods, mainly because of losses on the coupling circuit as well as on the transmitter and receiver side. The power transmitter is connected to the electrical grid by the means of an AC-DC converter, and it is magnetically coupled with the power receiver, which is often integrated within the portable device. The resonance circuit is the key element for power transfer, and it includes coupled inductors providing contactless power transfer. The amount of transmitted power is controlled within the power transmitter, but according to the information which are continuously sent from the power receiver back to the power transmitter on the communication link. In 2008, the Wireless Power Consortium has been built, and today over 100 companies have joined it, among which Nokia, Texas Instruments, and so on. And the WPG standard has been developed. This is a really binding standard, above all on the transmitter section and coupling circuit, while with regards to the receiver section, mainly informative guidelines are given, since the receiver is proprietary and integrated within the portable device. According to the WPG standard, the amount of transmitted power can be controlled by either the supply voltage or switching frequency control of the DC-AC converter, which drives the resonance circuit on the power transmitter side. Just as an example, this is the DC-AC output, the resonant curve, and the first harmonic of the receiver side signal. If a supply voltage control is implemented by increasing the amplitude of the DC-AC converter output, the first harmonic amplitude will be increased, as well as the amount of transmitted power. Otherwise, if a switching frequency control is implemented by lowering the switching frequency, the operating point will be shifted to the left, and therefore, again, the first harmonic amplitude will be increased, as well as the amount of transmitted power. Information about the battery state of charging power needs are continuously collected on the receiver side, and this information is encoded, and a sequence of bits is continuously transmitted from the power receiver to the power transmitter. This communication link is implemented by modulating the input primary coil current on the transmitter side, and again, the resonance circuit is the key element for signal transfer. The WPG standard gives only informative guidelines about load modulation techniques. So on the receiver side, the coupling circuit is alternatively loaded according to the bit which is being transmitted. Therefore, the impedance, which is effectively seen by the power transmitter, as well as the input primary coil current, will be modulated accordingly. If a resistive technique is implemented, an additional resistor will be connected or not to the resonance circuit according to the bit which is being transmitted. Otherwise, if a capacitive technique is implemented, an additional capacitor will be alternatively connected to the resonance circuit. And on the transmitter side, sensing and demodulation to be is implemented. These are system specifications according to the WPG standard. We have chosen an A1 design option. We have implemented an half-bridge topology and a switching frequency control within the range from 110 kHz up to 205 kHz, with a constant 50% of duty cycle as fixed by the standard. This is the SPICE model of a quite conventional architecture, which is used by most of the designers of wireless chargers, but spite of its extremely low complexity, as you will see by experimental results, this conventional architecture features a really poor performances in terms of power conversion efficiency. This is the transmitter model, which drives the resonance circuit. Which drives the resonance circuit on the transmitter side, and which is magnetically coupled with the power receiver by the means of two coupled inductors L1 and L2. Out of the resonant tank, a diode bridge is implemented in order to generate the DC voltage, which is suitable for battery charging. Resistive modulation is implemented by connecting an additional resistor in series with a switching and MOSFET, whose gate terminal is tied to the modulation signal coming out from the digital controller. So if the modulation signal goes high, the switching and MOSFET will be turned on, and the additional resistor will be connected across the diode bridge and therefore across the resonance circuit. Otherwise, the switching and MOSFET will be turned off and no additional resistor will be connected. Also, a capacitive modulation is implemented by connecting an additional capacitor in series with a switching and MOSFET, whose gate terminal is properly biased by this network. So, if the modulation signal goes high, the alpha PMOS will be turned on. Therefore, gate capacitances of switching and MOSFET will be charged, and they will be turned on, thus connecting the additional capacitor across the resonance circuit. Otherwise, gate capacitances will be discharged through the low side resistor, therefore switching and MOSFET will be turned off, and no additional capacitor will be connected. As shown by simulation and experimental results, the power losses on these topology are mainly due to the use of resistive modulation, first of all, and the extensive use of diodes and resistors. Therefore, we propose this power receiver architecture, by which resistive modulation is definitively avoided and only a capacitive modulation is provided. Then diodes and resistors are avoided and replaced by active MOSFETs, which work in the linear region, and so by selecting lower DSC-on MOSFETs, the power conversion efficiency could be heavily enhanced by this topology. This is a suitable architecture for AC implementation and a fully standard compliant solution. We have implemented a few-wave active rectifier stage by the means of a cross-coupled self-driven configuration. The self-driven configuration is implemented by ultra-low power comparators and drivers in order to speed up switching transients of both low-side MOSFETs, so further enhancing the power conversion efficiency, while power losses on ultra-low power components do not affect power losses of the whole rectifier stage. Just as an example, if a sinusoidal input is applied during the positive half wave, the output of inverter 2 goes down, thus turning off M4, while the output of inverter 1 goes high, thus turning on M3. Since M3 is turned on, the gate terminal of M2 will be tied to ground, therefore turning on M2. Therefore, the gate terminal of M1 will be tied to the output voltage rail, and therefore M1 will be turned off. So during the positive half wave, the input signal will be rectified through the cross-section M2 and M3. Since the circuit is perfectly symmetrical, during the negative half wave, the input signal will be rectified through the cross-section M1 and M4, thus achieving a full-wave active rectifying stage. This is the SPICE model of the proposed modulation network. The capacitive modulation branch is the same as in the conventional solution, while the bias network has been replaced by this active cross-coupled externally driven configuration. This network is driven by the modulation signal by the means of an ultra-low power dual driver, again to speed up switching transients. So if the modulation signal goes high, M5 and 8 will be turned on, and gate capacitances will be charged through M5. So switching and MOSFETs will be turned on, and the additional capacitor will be connected to the resonance circuit. Otherwise, if the modulation signal goes down, M7 and 6 will be turned on, so gate capacitances will be discharged through M7, thus turning off switching and MOSFETs, and no additional capacitor will be connected to the resonance circuit. From now on, experimental results will be presented. In green, you can see in the secondary coil current, in yellow, the output voltage, as you can see by fixing the load current and by increasing the switching frequency on the transmitter side, the output voltage as well as the output power on the receiver side could be decreased. In blue, you can see the modulation signal coming out from the digital controller, while in green, the primary coil current is shown. According to the modulation signal amplitude, the primary coil current is correctly modulated. From now on, a comparison between experimental results on the conventional and the proposed architectures is carried out. We have realized prototypes of both the conventional and the proposed solution, and we have tested both by the same power transmitter module in order to compare experimental results. We have forced a load current of 500 milliamperes, and we have measured the power conversion efficiency as a function of the switching frequency with both active and not active modulation. These are experimental results in the conventional architecture. The solid curve is referred to not active modulation, while the dashed one is referred to active modulation. So by the solid curve, by increasing the switching frequency, the output power will be lowered. Conduction losses are almost constant since a fixed load current is drawn, while switching losses increase as far as the switching frequency is increased. And this contributes to a decreasing efficiency as far as the switching frequency is increased. Since the conventional solution provides resistive modulation, with active modulation an additional current is drawn from the dead bridge, and therefore efficiency really drops if compared with not active modulation, as you can see by the dashed curve. But we have two opposite effects on the power conversion efficiency, since, again, as before, increasing frequency results in lowering the output power and so in a decreasing efficiency. But the additional current is proportional to the output voltage. Therefore, by increasing the switching frequency, the modulating current will be lower, therefore contributing to an increasing efficiency. And these two opposite effects are highlighted by the gap between these two curves, which is higher in the low frequency region where we have the highest modulating current values than in the high frequency region where the drop on the output power prevails and the two curves run parallel to each other. But above all, this conventional solution features really poor performances, efficiency drops below 50%, and above all, power conversion efficiency of the receiver stage is heavily dependent on operating conditions, operating frequency and active modulation. These are instead experimental results in the proposed architecture. Note that we have 1.5% of errors in these measures, but efficiency is really high and quite constant, quite independent of operating conditions. Just as before, we have that increasing frequency results in lowering the output power, and also introducing the modulating capacitor results in a lower resonant frequency. Therefore, with active modulation being equal to the switching frequency, the output power will be lowered. So altogether we have a decreasing efficiency as far as the switching frequency is increased, and the efficiency really drops if modulation is active and compared with not active modulation. But above all, the power conversion efficiency curve is really flat and independent of operating conditions. So after all, we have proposed a power receiver architecture for wireless battery charger, which improves the power conversion efficiency. So the conversion efficiency of the whole battery charger is now reduced to the coupling efficiency only, while power losses on the receiver side could be reasonably neglected. For future development, we are working on free space wireless charging in order to avoid contact between the receiver and the transmitter. So thanks for your attention. If you have any questions.
Thank you very much. Any question? Well, I have one. You talk that you define the efficiency as the ratio between the DC output power and the average power on the second coil.
Yes.
This efficiency is the same as in the other in the old systems based on diodes, or just you define this to decouple the magnetic losses from new power converter losses?
In such a system, the power conversion efficiency is defined as the power conversion efficiency of the whole battery charger, I mean from the transmitter down to the load section, and this is the overall power conversion efficiency. This is the product of two terms. The first is the coupling efficiency, so taking into account the magnetic losses on coupled inductors, and the second term is this power conversion efficiency of the receiver stage, so from the direct bridge input down to the load section. These two definitions are universal, and so
Thank you very much.